This is the battery electric shell project. The main goals of this project are design and model an aerodynamic shell for Shell Eco Marathon's prototype battery electric category, minimizing the weight and the drag experienced by the vehicle, and then confining a subframe within the shell that would support the driver and the vehicle systems in SolidWorks. Using data from previous research projects, the subframe seen in orange is created using 4 layers alternating micelle and 3K carbon fiber to support the driver during the infusion. The method is found to have a superior strength to density ratio, minimizing the weight while still supporting the driver safely. After finalizing the shell design, the model went into ANSYS to verify the drag forces and coefficients from SolidWorks flow simulation that was used between the iterative designs. The full shell and subframe were modeled to have an overall weight of 12.63 kilograms, which is 6 kilograms less than the current internal combustion engine shell frame concept. Then in ANSYS, the coefficient of drag was found to be 0.1174, which is significantly lower than the current internal combustion engine, which is at 0.155, and the design for the current UC shell, which is at 0.121. The next semester of this project will be finalizing the CAD for the 3D printed molds needed to manufacture this, and then creating a bill of materials for all necessary parts to complete manufacture.
This is the Urban Content Brakes Senior Design. The objective for this project is to design and manufacture a braking system for the UC that follows all Shell Eco Marathon rules and regulations. Some project goals and constraints. I wanted to research, ideate, design, and manufacture a braking system. The system needed to include 4-disc hydraulic brakes with a single pedal operation. Calipers and rotors have to be commercially available. We needed to incorporate a parking brake system, and the vehicle must be able to withstand a 20% incline. This is being tested with the main brake. We also needed to minimize the weight of the system as much as possible. Our goal is to have as lightweight system to have the highest efficiency possible. In the top right, the CAD you see is of the rear subframe. Incorporated in it is the rear caliper mounts, the rear caliper, the rotor, and the rotor hub. And then there's some FEA and some manufacturing work of the rear caliper mount. I designed and manufactured the pedal and rear caliper mounts. I also did the carbon fiber pedal with bended micelle foam, which is a big accomplishment. Some of those you can see on the right. You can see the full assembly of the CAD, and you can see my short process of vacuum forming a carbon fiber with micelle sandwich layers. Next steps for this project is we need to finish the manufacturing of the mounting brackets. That will be done this semester yet. In addition to this, we need to implement braking system into the vehicle. Mainly what we need to test is making sure the brakes are all operational, both the regular brake and the handbrake. The main brake needs to also hold the vehicle's weight on a 20% incline, and we need to machine the key weight on the drive shaft for the rear rotors. That's to adapt it onto the rotor hub.
This is the GX35 Heat Engineering and Airflow Tuning, or HEAT project. The main goal of this project was to improve the engine cold starting ability and overall competition efficiency through essentially a 2-stage approach. First, by adding an electric engine preheater and improving heat retention rates, and second, by optimizing the intake manifold geometry to better match the team engine, with the additional goal of improving sensor support for more intelligent tuning, all done with some basic shell rule and vehicle geometry constraints. Starting off with preheating and heat transfer, the first step was to do a fiberglass wrap around the engine. Using previous competition's oil temperature data, we see that overheating isn't much of a concern, and we're actually losing too much heat when the engine shut off during a coast. While adding insulation does increase the thermal inertia and how much energy is needed to increase average engine temperature, it retains heat better overall as seen in the graph. This also supports the preheating ability. We use a commercially available 50-watt silicone heating pad to accomplish this. Typically these use adhesive, but since this had to be removable, we had to manufacture an aluminum mount to press the pad up against the oil pan. The healthy operating temperature of the engine when running is 60 degrees Celsius, so the goal was to reach as close to that as possible. We did heat up and cool down testing of the engine under different conditions and figured out that when insulated, the preheater can accomplish a steady state of 50 degrees Celsius within the engine after about 40 to 45 minutes. Next is the intake development. Currently, the team doesn't possess a reproducible way to gather engine power output data, so to pursue improvement, simulation was used instead. This was done in a recursive sense, not to gain exact airflow simulated data, but rather to observe what trends come from changing specific geometries to know what changes we should make. For example, we can see that increasing the volume of the plenum trended towards also increasing the inlet air velocity. This was repeated on several parameters and informed what the final design would be. Accurate data was still desired, so we also implemented a MAF sensor to our system. This sensor originally only had an uncorrelated voltage output, so testing with the sensor on HVAC units with a known mass flow rate is performed to properly quantify the voltage to mass flow relation. How we did this is shown on the right here, where we used a known pressure differential to calculate a mass flow rate and then relate it to the sensor voltage. Give us the correlation value of the sensor in kilograms per second per volts or mass flow per volts. Final modeling of the overall intake includes a housing for the sensor, addition and subtraction design based off simulation data, and adaptations to other Supermileage projects like the new throttle body and electric throttle. So at the end, what are the final results? We accomplished the application of the preheating capability and process, as well as insulated the engine, preserve precious heat longer during competition. The intake redesign makes it more effective, tougher, and has some small additional tweaks to improve the system. One such example is changing the fuel injector bore diameter for better sealing and fitment. This new system also includes the calibrated MAP sensor, which provides incredibly useful airflow data that informs tuning and future engine improvements. In the future, this intake will need to be modified to interface when new custom throttle bodies or engines are created that would likely have altered connection patterns. Additionally, geometry can be improved greatly once methods like dynamometer testing are possible and observable changes are able to be made.
This is the prototype lean jackshaft senior design project. The project objective was to redesign jackshaft assembly components used to transfer the engine output to the drive wheel. In order for this project to be successful, it must be able to withstand the maximum forces applied to the system, maintain the optimized torque ratio of 16:1 between the engine output and the drive wheel, and it must be compatible with the current vehicle subframe. Some project goals include reducing the weight of the jackshaft components and improving the belt alignment between drivetrain components. Some foreseeable vehicle performance improvements as a result of this project include increased use longevity of the drive belts, decreased resistance between drive components, and overall improved fuel efficiency of the vehicle. From analyzing the current system, I determined that the largest opportunity for improvement lies within the jackshaft mount, as it is overbuilt, has numerous manufacturing defects, and makes belt tensioning difficult. The design process consisted of calculating the recommended pre-tension belt force for each stage, iterative CAD and FEA, prototyping to validate the designs throughout the process, developing a manufacturing plan, and developing CAM for machining. The Gates Power Grip Drive Design Manual provided me with a validated strategy to calculate the pre-tension belt forces for each drive stage, which were 47.9 newtons and 134.2 newtons. As you can see, the design was reiterated multiple times throughout the semester, decreasing in mass with each version. Along with decreasing the mass, the simulation was also improved to reflect what really happens within the system by applying accurate constraints, force magnitudes, force directions, and adding bolts to the assembly. The FEA simulation for the final design resulted in a maximum stress of 24 megapascals, which gave us a factor of safety of 10 and a max deflection of 0.007 of a millimeter. Throughout the semester, I've been gaining experience with the Haas mill, including use of the fourth axis. I manufactured two different parts, which were the redesigned jackshaft mount and a replica of the second stage drive gear, as the original was a proxy to the system and unable to be adjusted for belt alignment. Working through the jackshaft mount, the process began with facing the material stock, milling the flange geometry to the thickness of the mount, milling the bottom geometry to the same thickness, and finally clearing out the material left between the flanges. For the second stage drive gear, I developed cam for one tooth profile and programmed the fourth axis Haas to repeat the process after rotating the part until the entire profile was machined. Additional features were also machined, such as a keyway and set screws to secure the gear onto the jackshaft. Notable results from the project include decreasing the mass of the jackshaft mount from 601.4 grams to 247.2 grams, implementing a method to tension the belts by use of the slotted holes on the mount, installing an adjustable second stage drive gear for belt alignment, and finally benchmarking the recommended pre-tension belt forces for our drivetrain specs. Some of my next steps, along with possible work for the future, include installing the new mount onto the vehicle, testing the mount strength in a real-life use case, developing a drivetrain belt tensioning SOP to be used for future eco-marathon competitions, and optimizing the shaft diameter for additional weight reduction.
My project was the prototype hand controls. Now, the objective of this project was to manufacture hand controls out of a material that had a higher fracture toughness than PETG, which is the current material we use in our hand controls. And there were a few constraints that came with this project. First of all, the hand controls had to have a combined weight that was less than or equal to 84 grams. The hand controls needed a similar geometry. The combined total volume of the hand controls needed to be about 8.4 cubic inches. And the fracture toughness had to be greater than or equal to 2.3 megapascal root meters. Now, for the design process of this project, the first step was material selection. Now, using the Granta software by ANSYS, we found three candidate materials that seemed promising. That was oak, nylon carbon fiber blend, and carbon fiber. Additionally, FEA was used to determine the vulnerabilities in the hand controls, and it was found that the hand controls are most vulnerable just right above the base. Additionally, we manufactured a prototype hand control from forged carbon fiber and PETG molds, and the results were satisfactory as it yielded a solid, dense part, but also there was some difficulties in manufacturing as doing a forged carbon fiber part can be difficult to do. For the testing phase of this project, we relied mainly on mode 1 fracture toughness testing, where a testing specimen is put in mechanical tension and the test stops when the sample breaks. Now, there were 2 phases to the testing. The first phase was done on PET-G samples to determine the most optimal infill density and infill pattern to yield the highest fracture toughness, which can be seen. And the second phase of the testing was mode 1 fracture testing on the candidate materials and PET-G. Now for the results. Now from the first phase of testing, it was found that 15% density in a trihexagonal pattern yielded the highest mean toughness at 1.4 megapascals root meters. And then from the second phase of the testing, it was found that carbon fiber had the highest mean fracture toughness at 17.8 megapascal root meters. And then additionally, we examined the test specimens under a microscope to determine the failure modes of them. And it was found that PET-G failed due to brittle fracture, nylon carbon fiber failed from a ductile fracture, carbon fiber failed from a mix of delamination and fiber fracture, and the wood failed parallel to the grain due to a combination of tension and shear stresses. And the final recommendations from this project is that we recommend that the hand controls be made from nylon carbon fiber because it is lightweight, it's stronger than PET-G, and also using a nylon carbon fiber is much easier for manufacturing as it can just be used. You can just use a 3D printer rather than having to make molds, cut up carbon fiber, and do the whole layup process.
This is the electric throttle senior design project. This project focuses on replacing the current cable throttle system with an electric throttle that is controlled by a thumb throttle and actuated by a motor. The main reason for doing this is that the cable system does not give the level of precision and consistency that we want, especially for the vehicle where smooth throttle response is important. Through this project, I needed to better understand how a throttle position sensor works and how the ECU can use those signals to control throttle position. The design also had to stay compact enough to fit within the vehicle's existing layout, so packaging and integration were important constraints from the start. The way the system works is that the thumb throttle provides the driver input, and that signal is sent to the ECU. The ECU then interprets that request and commands the motor to rotate the throttle valve to the desired position, which controls the airflow into the engine. To make the system closed loop and accurate, the throttle valve position is measured and sent back to the ECU as feedback. That feedback allows the ECU to compare the commanded position to the actual position and make corrections, which improves throttle accuracy, consistency, and overall response compared to the original cable system. One of the biggest conclusions from this project is that motor sizing, gear ratio selection, and sensor integration all have a major impact on whether the system performs correctly. The design supports smoother and more precise throttle control than the cable system because it allows the throttle position to be electronically commanded and monitored instead of relying on mechanical linkage. Another key takeaway is that the system needs both reliable feedback and a motor that is strong enough to move the throttle while still being controllable within the application. The next step is to fully validate the final design on the vehicle under operating conditions and confirm that it performs reliably in real use.
This is the Throttle Body Optimization Senior Design Project. The objective of this project is to design and manufacture a custom throttle body that is compatible with our engines. The main goals are to reduce the overall weight and overhang length of the current throttle body and to optimize the airflow into the engine for better performance. This project will address key issues relating to throttle control, weight, and length, leading to better tunability and control in the throttle, as well as higher miles per gallon ratings and less stress on parts attached to the throttle body. The project began with research on throttle body design, aided by SAE journals and textbooks. Next, Pew matrices were used to determine the best possible materials for both the throttle body and valve. The best options found were 6061 aluminum and 300 series stainless steel for the body and valve respectively. Calculations were then determined to relate throttle diameter and the volumetric flow rate of the intake air. These calculations can be seen on figure 3 of this slide. Finally, a basic CAD model was created to visualize the basic design of the throttle. So far, the following tasks have been completed. Calculations for the throttle's throat diameter have been determined. Materials for the body and valve have been selected, with 6061 aluminum and 300 series stainless steel being the best options, and potential upgrades to a titanium throttle body in the future if time allows. Finally, the basic design of the throttle has been created. Next semester, this project will continue with final calculations based on airflow data from the 2026 Shell Eco Marathon competition, followed by final design and CAD, manufacturing, assembly, and testing. Thank you.
This is Clutch and Flywheel Overhaul Senior Design Project. The project objective is to redesign the OEM clutch and flywheel system to better suit the team's needs. The project goals and constraints are to implement pulley clutch, increase crank timing resolution by adding more magnets to the flywheel, add compatibility for a simpler backup starter system, reduce weight and unnecessary components. The engine still must fit within the same footprint as it currently does. And the starter motor speed must always be below engagement speed of the clutch. For our designed components, figure 1 shows our flywheel core and ring gear. The ring gear is 3D printed to mate with the starter and to include the magnets for increased crank position resolution. The aluminum core mates with this ring gear and is keyed to mate with the crankshaft. Those holes in the figure 1 flywheel core aligned with the holes in the figure 2 output shaft, which accommodates the pulley clutch in figure 3 and is keyed as well. The engine mount in figure 4 is modified to accept the new mounting points used on the engine. The results of our project, where we were able to implement the pulley clutch, we were able to implement the 8-1 magnet setup for increased resolution for crank position sensor. We enabled compatibility with off-the-shelf 206 electric starter motor as a secondary starter or backup for testing or at comp. We had a slight weight increase over the stock system from 1,866 grams to 2,038 grams, which is actually preferred by the due to increased rotational inertia by the starter system and the engine on idle. Next steps for this project would be further FEA to pinpoint where to cut weight, test different clutch engagement speeds, and to design alternative smaller flywheels for when starter motor is not in use.
This is the Rodfather Senior Design Project. Our project goal was to design and manufacture a custom connecting rod for the Supermileage Systems Enterprise vehicle. The primary objective was to significantly reduce mass while maintaining or improving strength and fatigue resistance. We targeted roughly a 40 to 45% weight reduction by transitioning from a steel rod to a machined grade 23 titanium rod. In addition to that, we performed benchmarking on the stock con rod, evaluated both 2-piece and 1P3 designs, and focused on developing a design that could be manufactured in-house. We explored several redesign concepts, including multiple 2-piece configurations using both 2 and 4 fasteners. However, the biggest constraint we encountered was crankcase clearance, which was extremely limited and restricted bolt size and placement. This created a trade-off between fastener strength and available space, making the 2-piece design less reliable. Thus, we selected a 1-piece titanium design, which eliminates fastener failure risk entirely while making it even easier to exceed our strength and weight goals. In the images, you can see the stock con rod concepts for the 2 and 4 fastener design, as well as the final printed prototypes for each variant.
So to validate our testing decisions, we performed several forms of testing. We first conducted OES composition analysis and Rockwell hardness testing to identify and verify the stock rod material properties. We then 3D printed prototype rods and physically tested fitment within the crankcase. To assess fitment, we manually rotated the crankshaft and checked for interference. We also used a caliper to measure 1.65 millimeters of clearance with the stock rod in place. This testing was critical in confirming that the designs were possible given the limited clearance, and is what ultimately drove our decision towards the one-piece configuration. For manufacturing, we developed CAM and Fusion 360 and designed a custom fixture to ensure repeatability. This was especially important because the machining operations had to be performed on one side of the connecting rod, and then the part needed to be flipped over and remachined on the opposite side. The fixture allowed us to maintain consistent positioning between setups so we could run the same operations without re-zeroing or adjusting our X or Y or Z offsets. With the fixture complete, we machined an aluminum prototype to validate our toolpaths and overall processes. Once validated, we transitioned towards titanium machining, which comes with a whole boatload of problems and challenges such as heat buildup, tool wear, and the constant need for coolant to prevent fires. Aluminum titanium nitride coated end mills were ordered specifically for the titanium due to their superior heat resistance and ability to prevent adhesive wear. The images show the workflow from CAM on the connecting rod to the machining process for the fixture and rod. So far, we have successfully iterated through multiple designs, completed benchmarking, and validated on our manufacturing process through an aluminum prototype. We also procured titanium stock and the necessary tooling to move forward with final production. Our biggest current limitation is the complexity of machining titanium, which requires careful process control. Moving forward, our next steps include machining the titanium rod, refining the two-piece design if needed, and ultimately press fitting the rod onto the crankshaft for full system validation.
My name is Josh Beatty, and I've been working on the Urban Concept Subframe project. The main objective of this project has been to design, optimize, and start manufacturing on the structural subframe for the team's new Urban Concept vehicle. The main goals have been to design a subframe that provides enough structural support for the weight of the vehicle and the driver, provides robust mounts for other systems like wheels, batteries, the motor, etc., is optimized to minimize weight, and it needs to fit within the existing shell design, which you can see on the right. Other goals are to develop a clear and effective manufacturing plan for the future work on the project and to start manufacturing the subframe. First, the material. Testing completed in a previous project shows that the composite material shown in the center left is ideal for this project. That is a micelle PVC foam core surrounded by carbon fiber. Micelle foam is an ideal material for this project because it is rigid but thermoformable, which means it is easily formed into both flat plates as well as molded parts. And then I used composite FEA techniques to model this material for simulation. So you can see in the center right the stack up of that material as well as the polar properties within that simulation software showing the material properties across its different directions. The results are I was able to use that to complete iterative composite FEA for a optimized lightweight design. I developed a manufacturing plan, and I've also designed molds, jigs, and patterns to simplify the manufacturing process. Some ongoing work is I'm working on manufacturing the roll bar and the rear firewall at this time, and that'll be completed by the end of the semester. And future work that will be completed in the fall is manufacturing of the floor and side panels, as well as assembly of the subframe with the rest of the vehicle.